Welcome back to Aircraft Structures 1 course. This is Professor Anup Ghosh from Aerospace Engineering IIT Kharagpur. We are at the beginning of the module 6 or the 6th week in sequence. The lecture number is 28. We have covered in last week lectures or last module lectures different way the stress, and in this week we will cover strain as well as we will solve a few problems to give you some insight about the analysis. So, we will discuss more on strain. This is a very important lecture. The lecture may outcome to a very small lecture, but it is very important. I would suggest if you are in the process of learning or in advanced studies, better you remember this particular lecture. It will help you, definitely it will help you. With that note, let us move forward, and as we move forward, the first slide comes with the recapitulation. It is always, I feel, better to recapitulate, that helps to memorize things, gives us the reminder what you have learned already, and as a whole at the end of the course you will see, if you look at this and attend this few seconds, you will find that you can visualize the total course very well, and that helps, that really helps. Not a big deal, but really helps. I have learned this from a very renowned professor. I am lucky to learn things from him. Anyway, so we have learned history of aircraft or aviation to some extent, and we have learned how physicist has developed the subject of mechanics, solid mechanics, and from there how the structural analysis has come up. In mathematical approach was the first approach that we have already started. We have started in last week as well as in the last to last week, while we have we discussed about complementary strain energy and total potential energy, everything we started, and those are the basic things where from the total subject has evolved to the date what we have learned. Various types of external load is the next topic we have covered for experienced by aircraft, and how those loads vary in different condition while it is in runway or it's airborne or maybe during landing. And we have also learned the flight envelope, load factors. We have also learned shear stress bending moments experienced by an aircraft. We have learned three-dimensional structures like trusses, and in the last week that is just in the last week what we have learned is that about stress, how the stresses are. We have come across different types of stresses, components of stresses. For isotropic cases, we have come across 6 components finally, considering the complementary shear stresses to be equal. Initially it was 9 components, and then we have come across of different orientations, transformations. From transformation we have seen that we can find a coordinate system or a set of stress sigma 1, sigma 2, sigma 3, which are normal stresses where known as principal stresses, where in those particular planes where those are acting there is no shear stress, and from there we have come across about shear stress also at any plane, and we have come across good examples like octahedral stress, and also we have come across about the stress ellipsoid. So, those things we have learned in the last week. With that note, we will move forward to the definition of strain. This week we will be covering mainly the strain. This is what already we have seen. So, what we are going to do is the strain, introduction to strain we will be doing, and I will try to introduce the strain with as much detail as possible in different books. It has been introduced in different way. I will try to follow a general approach with the concept of vectors and tensors. Let us see how do we understand that. Okay. So, in this it is again some mistake with the interpretation of slide. These are all vectors. So, with that note let us start our discussion. This figure is a really interesting figure. What we are trying to see is that a vector is there as r, the tip of that vector is p, and an incremental length of that p vector is q, which is given by dr, and we see that we are considering that amplitude dr is equals to ds. Now, we also define dr star. Please consider that thing for misrepresentation in digital media. Similarly, we are considering that after deformation, deformation means it is under stress from external system, and because of the stress that r vector has come here, and that p has changed position to p and q has p star, and the q has changed position to q star. And please look at that, there is twisting and all other possible change of lengths as far as possible is represented in this figure. The overall this figure is changed, it is twisted, it is length is increased, all those things, all possible ways we have put here. And from general consideration, since you are introduced with the components of stresses, we can easily imagine that many components of strains are also there. And we define that this r vector as the r p as x p I, x p j, x p k, or x 1, x 2, x 3 as I j k using the unit vector. Now, as it is said there, I mentioned that delta r is an increment from here, and that is the point q, x plus d x I is are the 2 points to a distance of d r. Apart, and that d r apart, these 2 points are changing to these 2 points, d r changes to d r star, and because of that the displacement involved is here is u and here is u plus delta u. Let us try to see what happens. This is a general discussion on the direction cosines involved, and we will be using the direction cosines. That is the reason direction cosines of p q are lambda 1, lambda 2, lambda 3. Sometimes it is given by LMN, sometimes if it is unit n 1, n 2, n 3, all those way it is given. And that is the reason it is given as dr is ds, the x y z as it is can be said x 1, x 2, x 1, x 2, x 3 here, and similar way we define those in a general way we define this way d x I is equals to lambda ds. After deformation, the displacement of p from p to p star, this we have said, and u is E I, U I, where u are 1 again. It is some similar terms are introduced here, though we will be using mostly the tensorial way, but these terms are introduced, these or these are introduced to give you the correlation with the already experienced or learned system. We are bringing back all those things again and again. So, in that way 1, 2, 3 represents u, v and w are known as engineering notations, and displacement of q is, as we mentioned, u plus u star is equals to u plus delta u. So, with this understanding of the system and positions and vectors, direction cosines, we move forward to the next slide. All vectors are now ownerless. So, we need to erase those vectors. Okay, vectors are erased. Okay. Now, what we have is that this is the increment u star. Yes, it has gone back, that is the problem. Okay. So, u star, as we have seen, that is getting increment with respect to the coordinate system, or that is the way, this is the gradient in that particular direction of x 1, and that is why the dx change is given as del u 1 by del x 1, del u 2 by del x 2 by dx 2 in the y direction, x direction, y direction and z direction. In 3 orthogonal direction, we are giving the increment, and that is consisting of the du portion, and then du gets redefined in this term this way as the separate increments of that particular direction or 3 orthogonal Cartesian directions, and accordingly what we have is that u star I minus u I is equals to this. So, with this what we have, which represents the relative displacement between the two neighboring point P and Q. A small line element dr before deformation deformed to dr star. This we are repeating. Then the magnitude has changed from ds to ds star, and from the usual definition of strain, this is has come close, please excuse me. If we define epsilon is equals to change of length by original length, that gives us ds star minus ds divided by ds, and a simple algebraic plus 1 if we do in both sides, we get this relation, which gives that ds star or the changed length, this length is equals to 1 plus epsilon multiplied by the ds, the original length. Now, ds star amplitude, if we are talking about, is nothing but the dot product of these two p q and dr star and dr star. So, what we can do is let us see how can we define that p q. So, So, this is star component, this is star component, that is the reason we will come there. Okay, so, p q star, what we have found is that r q, a vector I have not drawn from here to here, and a vector r p star, that is from here to here, that is the difference, will give me that p star q star vector. So, that is written here and it is expanded as r p plus d r and u plus delta u, and this is the r q what we see and this is the r p what we see, and if the common terms cancels out and we have that this is equals to d r minus d u. And actually while we substitute the values of this, what we have is that this is equals to dot product of these two, or in the other way if we see that this is equals to p star q star dot p star q star dot. So, this we have as this expression and those expressions are substituted here, and in the previous slide what we have already found out, that is put here. And what we see is that I have skipped some steps in this, because that is a completely tensorial notation of multiplying two incremental vectors. We need to already you see some are introduced, Kronecker delta because of the dot product is already introduced, and because of the introduction of that dummy variable k, l, all these things, there is a complicated tensorial calculus is involved. That is the reason I have jumped those few steps, and why if we see we get, if we carry out this, we get these equations, and the equation becomes that del x dx I multiplied by dx I, or square of it, we generally do not write as square in that sense. So, the other components becomes del u I del x j, del u j del x I, del u k del x I, del u k del x j, these two are repeated. So, if these two are repeated, what happens? We will have summation over that, but before that let us see how does this get modified with respect to the left hand side. So, now d s can easily be divided on the right hand side, and we can have that this is equals to lambda I to lambda I, and this is also lambda I and lambda j, this is x I and x j, that is the reason I j, and this is x I, and multiplication of this or something like cos square theta plus cos square alpha plus cos square beta plus cos square gamma is equals to 1. So, following that for 3 dimensional case, we have direction coefficients summation of those equals to 0. This and this cancels out, the remaining term is twice E plus epsilon, twice epsilon plus epsilon square is equals to this term. So, finally, what we see is that we considered a vector r, and that vector is changed position to here as the final r vector with p star, and associated increment of that particular vector dr is also changed to dr star, and that thing we have found out that what is the strain. This is the strain from here d s star square we have found out, and d s star square is nothing but this p q dot product of these two, and those two vectors we have found out dot product using the tensor calculus, and we come across some relation with respect to the strain and displacement variables involving u I, u j and u k, sorry u I j, where I j varying from 1 to 3. So, with that note we move forward to the next slide. Yes, this is what we have seen in our last slide. It is written in a very clean way. Now, epsilon square may be neglected as a very small value. Please consider this epsilon and this epsilon as same. These are two font problem only. So, if this is neglected, because very small terms if made square, that contributes very small way, that is the reason that is neglected. And if we express that epsilon is equals to epsilon I j lambda j, what we can see that this epsilon I j is equals to half of u I comma j, that means the derivative of u I with respect to j, derivative of u j with respect to I, and derivative of u k with respect to I multiplied by this and summation. To understand this tensorial notation, one example is carried out. In this example, I and j is considered as 1. So, what happens? Half remains outside as half. This is 1 comma 1, that means del u 1 del u del I or del x I. This is said that del u, again same quantity because both are same, and there here we have summation of those. These are, since it is 1 all are coming as square, but it is not always the same way. We can elaborate it, we can experience it. So, I would suggest you may consider that as a homework. If we elaborate this as a tensorial notation, putting I and j 1, 2, 3, and k is definitely sum over I j, and since it is repeated, we need to consider those as sum of those two terms. Let u 1 equals to u 2 equals to v, and u 3 equals to w. Then this same expression becomes this expression. So, it is in index notation 1, 2, 3, it is in Cartesian notation or x y z notation u v w. U v w are the displacement fields, and derivatives are taken with respect to x, and epsilon x x is defined this way. Now, here it is better to introduce that probably you were introduced with the term that epsilon x s is equals to del u del x, where from this term comes. This is what we get because of consideration of that particular generic case of strain derivation. We considered any type of movement, and we have in that way we have considered some higher order terms or nonlinear terms. So, this part of strain is generally known as the nonlinear strain, and this is known as the linear strain. So, in a general way, if we write it down what it looks like, let us say if it is some shear strain to be denoted. So, like that epsilon x x, considering 1 2 also you can find out, and as I said it is does not is a square, it is sometimes this way written, and in general epsilon x y is something like half of del u del y plus del v del x, that is what we are familiar with. But these terms are coming here as the nonlinear terms. For linear theory, we generally do not consider those terms, and it becomes something like epsilon x x equals to del u del x, y y is del v del y, z z del w del z, and x y is equals to half of del u del y plus del v del x, and similarly we can write the other strain components also, where there is a good relation between these two. epsa, and it is known as gamma 1 2 is known as the engineering strain, and epsa 1 2 is known as tensor component of strain. So, please keep it in mind, generally these two convention is followed, either epsilon or gamma is used, and with this notation we will again. Yes, please stop, please recording.
Plus or multiplication del u by del x plus del v u by del y. I think
It is multiplication. Yes, হ্যাঁ একটু স্টপ করতে হবে, এই স্লাইডটা গন্ডগোল হয়েছে। Last slide what I have written, yes, here it is written square is considered, there it is written, yes, good pointed out, good pointing out. So, better to repeat this slide. এই স্লাইডটা রি-রেকর্ডিং করতে হবে, একটা মিস্টেক আছে। হ্যালো, হ্যাঁ এই স্লাইডটা রি-রেকর্ডিং করতে হবে, এখানে একটা মিস্টেক আছে। হ্যাঁ, এটা স্লাইড নাম্বার 9, এই যে 9টা অ্যাকচুয়ালি এই এক্সপ্রেশনটা ভুল লেখা হয়ে গেছে। হ্যাঁ, আমি এক্সপ্রেশনটা ঠিক করে দেবো তাহলেই হবে, আর কোনো কিছু নেই। আমি এখনই আর ওই এক্সপ্রেশন নতুন করে কারেক্ট করে আনবো না, আমি এখানেই পেন দিয়ে কারেক্ট করে ছেড়ে দেবো। হ্যাঁ, কারণ ও করার অত সময় নেই, এ নেই, এই প্লাসগুলো মাল্টিপ্লিকেশন হবে, প্লাসগুলো মাল্টিপ্লিকেশন করে ছেড়ে দেবো। হ্যাঁ, আপনি স্টার্ট করে দিন। এক মিনিট আমি পরের স্লাইড, একটাই স্লাইড আছে সেটা দেখে নিই ভুল আছে কিনা, না ভুল নেই সেটাতে, ঠিক আছে। হ্যাঁ, আমরা শুরু করি, আমরা এখান থেকে শুরু করি, আর 2-3 মিনিট হবে দিয়ে শেষ করে দেবো। So, with the generic derivation of strain, we have already seen the epsilon xx considering from the index or tensorial notation to the Cartesian notation, how does it changes to epsilon xx. In case of epsilon xy or the shear strain, similar way we can derive from the index notation what is the expression comes. It comes as half of del u del y plus del v del x, and this is not plus, please note that it is a typographical mistake, this is multiplication, this is also multiplication, and this is also multiplication. Do not think that it is deleted, these plus signs have come by mistake, but actually if you observe the previous expression you can also easily get, but for correction purpose it has been corrected here. And what we do, we move forward considering this particular portion or the nonlinear portion, as it is said to be discarded for linear theory, and most of the derivations, most of the work whatever we do, we follow the linear theory, and probably our world is running following the linear theory. Whatever engineering design in general we do, we consider linear theories. Nonlinear theories are still in research state. Implementation probably is there in some cases, but it is not maybe very high precision strain wherever it is required, or the material which shows too much deformations along with non-linearity in its deflection. In those cases we need to consider, but those are rare cases, we generally do not need to consider. One very specific example may be the inflatable structure people are using, but anyway those things are very high topic of discussion, better not to bring here at this stage. So, anyway what we see is that with linear theory it reduces to very easy expressions, epsa x x is del u del x, epsa y y del v del y, epsa z z del w del z, and epsilon x y is equals to half of del u del y plus del v del x. Similarly, the y z you can do and z x also you can do is corresponding u v and w are all these variables will change, and corresponding one more notation is generally followed, that is half of gamma 1 2, where gamma 1 2 is known as the engineering strength and epsilon 1 2 is known as the tensor component of strain. So, we move forward. So, we come across to the last slide. It is better to remember this slide. This slide is very useful wherever whatever you do. You may you may like to remember, along with the nonlinear terms, or you may like to remember without the nonlinear terms, but it is better to remember this. If you remember all this up to this, there is not a big deal to remember the remaining portion. So, this is what the strain is defined including the nonlinear portion, and it is only with the linear terms. So, with that note, let us conclude today's lecture. Reference slides are same, and we come back to the what we have learned slide. In that learned slide, we have learned linear and nonlinear strain derivation with respect to the displacement, strain displacement relation. Strain displacement relation is learned. Now, we will go further with different compatibility equation of strain, and we will solve problems in our future lecture. So, with that I thank you for attending this class, this lecture. We will meet again in the next lecture to start or to talk more about strain and problems. Thank you.